Stable. Stabilisation of the turtle. All right. So today we would like to look at the stabilization of the trace formula for SO2. And I'll start by writing down the pieces of the trace formula. So what should the trace formula look like? So it's two different expressions for a distribution, and I'll first explain this piece, and then I'll explain that. So let's call this the geometric side. So the geometric side has a number of terms. I'll give them names. So the first term will be the central term, and it is just going to be the sum of the values of f at the two central elements 1 and -1. There are volumes in front, the Tamagawa numbers, but since SO2 is simply connected, this is 1, so we don't have to write it. Then we have the regular elliptic term, and this one we have already seen a couple of times, so it's going to be a sum over gamma in G of Q, regular elliptic. There's a volume term, and then there's an orbital integral term. And then we have the hyperbolic regular hyperbolic. So again, it will be a sum over gamma. So this is up to conjugation, of course. Sum over hyperbolic elements. Well, what are the hyperbolic elements? These are just elements in the diagonal maximal torus. And up to inversion. That's what the conjugation would be for those elements. And then we have the volume here. Well, we could even put it out front. And then we have the weighted orbital integral. So the weighted orbital integral there will be a weight factor here. This is over the split diagonal torus. And so the weighting factor is itself a sum over local weighting factor. So that would allow you to write this down, write this as a sum. So we can take this and write it itself as a sum over places. There we're going to have a local weighted orbital integral. Maybe unfortunate there is V sub V. And then a product, so this is the sum over places, and then this is a product over places that are not equal to that place of unweighted usual orbital integrals. We're getting into some competition here for Revere with the turtle. And so this is the hyperbolic part. And then we have a unipotent part. Okay, so in principle, what the unipotent part would be just the unipotent orbital integral. So G of A modulo the centralizer of a unipotent element. We'll be summing over unipotent elements. Well, what should qualify as a unipotent element? It's something that's unipotent up to a center. So we actually have two sums here. One is A equals plus minus 1. These are the central elements. And then one is U, which is a rational number up to squares. These will be the unipotent classes. And then we'll be doing this, NA G dg, where NA, well, let me write NA. NA is what you, well, NA comma X, or I guess I called it U, NA comma U. NA comma U is A, which is plus or minus 1, 1 U 0 1. Okay. Now, the trouble is that this actually diverges. So this orbital integral that you'd like to have in the trace formula is not there. Each local piece converges fine, but for almost all places, this test function will be the unit in the Heck algebra, and then the unipotent orbital integral at that local place for the unit in the Heck algebra is basically the local L factor at 1 for the zeta function, and so their product would give you the pole. So this is not what we really have, but you have a regularized version of that. And the way the regularization works is you put in a certain term here, beta. So what is beta going to be? I can explain this. Okay. So beta of G is equal to the square of the absolute value of A, where A comma A inverse are the eigenvalues of the toral part in the Iwasawa decomposition of G. Okay, so you write G as G is NTK, and then T is a diagonal element with entries A and A inverse, and then you take the absolute value of A squared. So this is now parameterized dg. This is now a function in terms of the complex variable S, and it is, you'd like to evaluate it as S equals 0, but there it's going to have a pole precisely like the zeta function has a pole. So what you do instead is you take the constant coefficient of the Laurent expansion at or around S equals 0. So the Laurent expansion will have a simple pole there with some residue, then it will have a constant coefficient and it will have higher terms, and you take the constant coefficient, and this is the unipotent contribution to the trace form. Okay. So we can and will rewrite this in a little bit as follows. So what we can do is we can define the following function, theta as f, which is going to be, we're just going to take the zeta function at s plus 1 inverse, and then this part here. Okay, let me not do the sum, let me just take the integral alone. So maybe I should put here, maybe I should decorate with A and X. Let me not put them in there, it will depend on that. Okay, and now these poles cancel out just right. So this thing is going to be analytic at S equals 0. And so you can do a very simple computation to work out what the constant term of the Laurent series expansion of this integral is without the sum. Namely, if you write zeta of s plus 1 as, well, whatever the residue is, if it's q, it will be 1, but if it's some other number field, it will be something else, over s plus 1 plus lambda 0 plus higher terms. Sorry? I shifted here. Sorry. I shifted already in here. Thank you. So then, the unipotent term is going to be up to the sum of a and x is going to be lambda inverse, and let me, because I don't want to apply the product rule in real time on live camera, I'm just going to write this up. This is what it looks like. Okay, so this is as far as the geometric side is concerned. The same central elements, and then square classes. I think I call them U square classes. Okay. Now we come to the spectral side. And on the spectral side, we also have a number of terms. First of all, we have RF, which is the thing we're really after. This is just the trace of f on the discrete spectrum. But then we have supplementary terms. One of the supplementary terms, so I'll just call this R. Let me call this continuous dot 0. This is going to be a discrete contribution to the trace formula coming from the continuous spectrum. This is exactly what Ali was talking about in the previous talk. And this is going to come from the following. We're taking the sum over all characters. F is Q for me, which are sign characters. So we're taking the sum over all sign characters. And then the contribution is the following. Well, there is a constant. I'll stop paying attention to such constants very soon because there will be too many terms to deal with. But this is the contribution. As you can see, it's a discrete contribution because you have a sum. However, it comes from a continuous spectrum. What are the terms here? This rho eta is simply the parabolic induction of this character, and then m eta is the standard unnormalized intertwining operator. So m eta is going to be the intertwining operator defined to go from rho eta to rho eta inverse, but rho eta inverse is rho eta now because this is a sign character. And this is defined in the usual way as the integral over n of, well, this applied to some element in this induced representation is the integral of phi w u g du. And there is the usual, there is the convergence issue, so it has to be analytically continued and so forth. And then we have two more terms coming from the continuous spectrum, which contribute continuously to the trace formula. So one of them is the following. We're going to integrate over a space. I'll say in a moment what it is. And then, okay, so the space here, D0, is all unitary characters of AF cross mod A cross, and this as a space is a disjoint union of components, and each component is, if you like, a copy of the real line. So R acts on D0 such that S, well, let me say eta sub S. So if you have an eta in D0 and an S, this is going to be eta times absolute value to the 2is. And so this action of R on D0 endows D0 with a measure, namely it transfers the Lebesgue measure on R to each component, and then with respect, this is the measure that we take. And then finally, we have continuous term number 2, which has a similar shape, but it's going to involve derivatives of intertwining operators as well. Yes. So we're summing over all places. This is the local contribution at the place V, and then at the places that are different from V, we have just the trace of the induced representation without the intertwining operators. Okay. So what is this intertwining operator R? This is the normalized version of the standard intertwining operator. So R eta, or R eta V, this can be done locally. This is the epsilon factor and then a ratio of L factors times the standard unnormalized intertwining operator. Okay. So these are the terms. And now, so we have the geometric terms, we have the spectral terms, and we would like to take this whole thing and stabilize it. What does that even mean? Well, in fact, none of these distributions is even invariant. If we replace f by a conjugate of itself, the value of this distribution is going to change. Even so, not only are they not stably invariant, they're not even invariant. So we're going to manipulate them in the hope of trying to make them stably invariant. And in the course of the manipulation, what we're going to discover is that eventually we'll have to leave behind the notion that the trace formula is an equality of a geometric side and a spectral side, because the stabilization is going to require us to take terms from the one side and put them onto the other in order to create something that's stable. This already happens if you want to make the trace formula invariant, and so in the stabilization it's even more pronounced. Okay, so let's start. Okay. Well, the first step is very easy. We look at the central terms. They're already stable. We're done. Very good. The next thing is we look at the regular elliptic terms. Well, there is a lot of work involved there, but we did all of that work already in the first lecture. So let me just remind you. Stabilization of the regular elliptic term. So we called it back then trace formula of regular elliptic, by which I mean this sum here. And what we found out is that it can be written as a stable version plus a sum over endoscopic tori of, well, almost all of the, I write stable trace formula, almost all of it, but really the G regular terms. So there were two terms in this trace formula for the torus that were missing. Okay, so this was the result of the first lecture. And so now we continue. So this distribution is, of course, stable. It was stable by design. But what do we make with this distribution? Of course, it is not stable. It's the error, the difference between this which is not stable and this which is stable. So what can we do with this? Well, at the moment, there is nothing you can do with this because it's not really anything. It wants to be the trace formula for a torus, but it isn't yet because it's missing some terms. So our next order of business is to somehow go fish in the other terms of the trace formula for G and find the terms here that we're missing. So let's first have a look at what are these terms that we're really missing. Okay, so this will be called completing STF torus FT. Okay, so we're missing Ft of 1 plus Ft of minus 1 up to some volume factor, namely the Tamagawa volume of Tf. Well, can we say what this really is? I kind of mumbled a little bit last time that we have a definition of Ft for all G regular elements, and then you can show that it extends smoothly to the singular elements. But I didn't really tell you how. I just told you, well, you have to modify it. You had a naive Ft, and then you had to modify it locally at all places, and then it extended smoothly. But now we have to actually look more carefully at exactly what the smooth extension is. What is the value of it? So let's recall, FTV, so at a given place, this had a somewhat longish expression. So there was the Langland's lambda constant here. There was this kappa V, which is the quadratic character of this local quadratic extension. Then we had the usual Weyl discriminant. And then we had the naive. Let me call this, remind you of the notation that we had naive of gamma V, which was just the plain difference between the two orbital integrals. So that was the orbital integral at gamma V FV minus the orbital integral, maybe let me call it EV here, and then EV bar FV. So that was naive. Okay. So now we have to look more carefully what happens when we let gamma V or EV alternatively go to a singular element. And I'm going to give an example calculation of this. I think this will have to be eaten now. I tried my best, but it just looks so tasty. Okay, so here is an example computation where V is the infinite place, and I'm looking at gamma V goes to 1 instead of minus 1. Of course, the computation for minus 1 is very similar. All right, then I'm going to write the following, which is a direct computation. You can find it, for example, in the book of Tony Knapp, but it's not something that I want to do on the board here. So this is what an element in the anisotropic real torus would look like, e to the I theta, because this torus, its real points are a rotation. So this is going to be the following: the integral from 0 to infinity, and then the integral over k, the real maximal compact, f of k, 1 u 0 1 k inverse dk du. Okay. And so a very simple substitution will tell you what happens if you approach 0 from the other side. If you approach 0 from the other side, you're going to get something else. So this is getting into the jump singularities of the orbital integrals. You're not going to get the same result as if you approach 0 from this side. You're going to get something that has a similar formula with the following subtle difference here. Okay. And so you can imagine that you can easily choose a test function for which these two integrals are different. That would witness the jump singularities, which is why we had to introduce this sign here in order to make it possible for this to have a smooth extension. Okay, so now then that means that the limit as t goes to 0 of this renormalized naive, ft naive here, at EV or EI theta, is going to equal the following. It's with the integral from -infinity to +infinity, and then we'll have the sine of u, and then we'll have the integral over k, f of k 1 u 0 1 k inverse dk du. Okay. The sign comes from the fact that you take this half and then you take minus that half because you're taking the difference of these orbital integrals. Okay, so now look here. What do we have? We're already integrating over k up to conjugation. Now, what is this 1 u 0 1? Well, it's the conjugation of 1 1 0 1 by a diagonal toroidal element, u1. So this is also really an integration, even though it looks like a real integration over a line, it's an orbital integration. And then k times t is what happens when you take the group and divide out by the centralizer of the unipotent element. So we can write this actually as an orbital integral. So putting this together, what you're going to end up getting is the integral over PGO2 FV, FV's R now, modulo the unipotent group, and then here you have the sign of the determinant of G, f of G inverse gamma G dg. So this is what you get. Now, what is sine? Well, that's just, I mean, of course you know what sine is, but the point is that this sine is what we called kappa infinity. This is what local class field theory associates to the quadratic extension C over R. In other words, this is the kappa that makes a kappa orbital integral. So this thing here is a kappa orbital integral, a unipotent one. So here is the moral of this computation. Regular elliptic kappa orbital integrals degenerate. They were giving Ali grief last time for spelling. Degenerate to unipotent kappa orbital integrals. And this works actually for every local field. So let me just write down the corresponding formula. The limit as gamma v goes to some AV, which is +1 or -1 central element of this non-naive thing, FTV gamma v, is going to be equal to the kappa unipotent PGL2 FV, kappa V, that GV, f of GV inverse gamma V GV. Okay. Good. Sorry? Gamma is 1101. That's right. Maybe sorry, let me call it, let me use my notation n sub a, which I introduced. So the a is here, n sub a is the ±1 central a times n. Okay, so what does that suggest? That suggests that if we want to find these missing summands, we should be looking at the unipotent contribution on the geometric side of the trace formula, analyze that, and hope to find this same thing over there. Okay, so all right, well, we had written the unipotent contribution. It was a sum over central elements and then a sum over square classes. But we can repackage this with an elementary calculation that I'm going to skip. We can repackage this slightly in the following form that looks very similar. We're going to introduce the following group G prime, which is going to be all elements in GL2A whose determinant is contained in Q cross times A cross squared. Okay. And then we can write the unipotent contribution. The sum over central elements and over square classes is going to go away, and it is simply going to be the following. It's going to be the integral over Z prime, which is the center of G prime. And then it's going to be just this. Well, it's going to be the constant term of the Laurent series expansion at s equals 0 of that fellow. Now, why did we make this computation? Because this is going to allow us to introduce the kappas into this term. Namely, we observe that the ideals modulo this group here, Q cross times A cross 2, this is a compact abelian group. And the integrand here is defined on all of GL2A. And so using the exercise that I noted last time when we were discussing the stabilization of the regular elliptic part for a general group, we can write this, we can decompose this entire function into characters of this compact abelian group. Okay, so we can write this here as sum over characters of this compact abelian group. And then the integration is going to now go over PGL2A modulo NA of that same expression, but with kappa that G put in. Okay, now how is that useful? Well, it is useful because now we can look at individual kappa contributions. That's something we didn't see from here. Using this procedure, we were able to chop this down into pieces. So let's look at the contribution of one kappa, which is non-trivial. So take kappa non-trivial. Well, if we take a non-trivial kappa and then look at this integral, a very similar computation from the one that I alluded to that told us that the adelic unipotent integral diverges because it would give you the L value at 1 of the Riemann zeta function. The same computation is going to tell you that for a non-trivial kappa, this, well, the local such orbital integral at the given place is going to give you the local L factor at 1 of the L function for the kappa V. So let me write this down. So we have a computation here that says that if you do the local integral of kappa V that GV and then FV of GV inverse and I don't know, let's do N GV beta GV minus S dGV, that this is essentially, up to some constants depending on the measures you've chosen, going to give you LV1 kappa V. And so the basic observation is that the global L function Ls kappa has no pole at S equals 1. Yes. And so that means that the thing that prevented this unipotent orbital integral from existing just without a kappa is now gone, and putting a kappa in tells you that the adelic orbital integral exists as it is, or in other words, the constant coefficient of the Laurent expansion at S equals 0 simply equals the value here. Okay, and so that, of course, if we put an A here, we're going to have FV of A here. Okay. And so then, but now notice that this this is exactly what we wanted to get. So let me write down the final upshot of this particular computation. We see that for kappa not equal to 1, we get L1 kappa times the product over V, L1 kappa V inverse, and then the local unipotent kappa orbital integral, which by the previous computation is exactly the thing that we were expecting. Okay. So where do we stand now after this computation? Let's recap. Yes. But the point is that this L factor, I was a little sloppy. I neglected to put the L factor here, which occurs from switching between, as Julie explained to us, the geometric measure and the normalized measure, which is used in the measures. And so this part here matches exactly with what you want to have here. And then you have the global L factor, but this is going to be the volume of, which is the thing that occurs in the trace formula for T, in front of ft1 and ft minus 1. Okay, so let's recap. Now we have equality of the following distributions. On the geometric side, we still have the central pieces that we have not touched. We have 1/2 the stable trace formula, regular elliptic for G of F. And now we have the full stable trace formula for T. The G regular has gone away. We just put in the singular terms. We still have hyperbolic. And we still have the unipotent part. The one piece that we have not dealt with was the piece where kappa is equal to 1. So this is what we have on the geometric side. And we haven't touched the spectral side. So let me, just to save time, not write down and spectral side. It is unchanged at the moment. Okay, so now we look at this and say, how far have we come towards our goal of stabilization? This is stable. This is stable. This is, of course, still not stable. We worked so hard to complete it, but of course it's not going to be stable. And then who the hell knows what's going on here? But the point now is that because this is the full trace formula, it has itself two sides, the geometric side that we have so far used to manipulate it, but also the spectral side. And so we're going to use this now. We're going to use the fact that the stable trace formula for a torus at Ft has the spectral side, which is the sum over O theta of theta Ft. So we're going to take this piece here, and we're going to move it down to the spectral side, and we're going to work on it there. So what are we going to do with it? Well, remember the discrete contribution of the continuous spectrum on the spectral side. It was a sum over sign characters. And it is exactly this that we're going to relate to this. So let's see how this works. So treating the unstable part, this is the next section of our discussion, of the term continuous zero, which was the discrete, the contribution of the continuous spectrum to the discrete part of the trace formula. Let me remind you what this term is. It's -1/4 trace m eta rho eta f summed over eta quadratic. Okay. Now, the trace of rho, so let's think what a summand does in this situation. So remark, rho eta is the restriction to SL2A of a representation of GL2A. So its trace is a stable distribution. However, this intertwining operator might act, so this is going to generally be reducible, and the intertwining operator might act in different ways on the different irreducible pieces, and this is what's going to make this generally unstable. So this is what we're going to try and understand. Okay, so for this we're going to use the normalized, we're going to replace the unnormalized intertwining operator by the normalized intertwining operator. So we're going to rewrite this piece here as -1/4, and then we have L eta inverse over L eta trace R eta, and then rho eta f. I just put in the formula I inverted the formula defining the the normalized intertwining operator. So now we have two cases. When eta is trivial, then the normalized intertwining operator is going to act as the identity. Now, this is, so I'm going to start pulling out of my hat, or I have been for a while, a lot of local computations that are performed by Lebesgue and Langlands, and I'm just quoting them because they all take time and they're all involved. So this is one of them. When eta is 1, the normalized local intertwining operator acts as the identity. So the entire summand is stable. Now let's look at the non-trivial sign character. Okay, now consider eta not equal to 1. All right. Well, if eta is not equal to 1, then it is going to give us a quadratic extension E over F by class field theory. Okay? And so thus an endoscopic torus T. Now let's consider the trivial character of this torus. Okay, so this endoscopic maximal torus can actually, its L group can be embedded into the L group of G, in fact, in a canonical way, because SO2 is such a simple case. On the other hand, this character gives us a Langhans parameter, which we can continue here and get a Langhans parameter. And even though this character was trivial, when you compose with this canonical but non-trivial L embedding, you're going to get some non-trivial Langhans parameter here. Which non-trivial which packet corresponds to this? Well, locally, an adelic packet is a product of local L packets. So at each local place, so at each place V, the L packet, how should I call this? Theta, L theta V or something like that. The L packet pi L theta V consists of the irreducible constituents of this principal series representation. And then here is another local computation. The normalized local intertwining operator. And so what are the irreducible constituents of this? Well, it turns out there's two of them, and we can call them pi plus eta v and pi minus eta v. Well, sometimes there is two and sometimes there is one. And if there is only one, let's imagine this isn't there. Let's call it 0. And if there is two of them. But in both cases, what I'm going to write down will be true. Our eta v acts on pi plus eta v by plus 1 and acts on pi minus eta v by minus 1 if pi minus is there, and otherwise this is not to be read. So the trace of R eta v rho eta v f is going to be pi plus eta v of f minus pi minus eta v, well, we're doing local, fv, fv. And this has got to remind you of something. This is exactly one of the two sides of an endoscopic character identity, an endoscopic character identity for this particular endoscopic torus. So by endoscopic character identities, this equals exactly theta v of ftv. In other words, the piece that you see here. And so the upshot of this discussion is that the part of the trace formula here for the non-identity character on the spectral side cancels exactly the part of the term continuous 0 for all the non-trivial characters. So let's write this down. Let's write a summary of where we find ourselves at the moment. So recap. We have the equality of, we still have a geometric and a spectral side. We haven't quite left that realm, even though we moved something from the geometric to the spectral side. The two sides are still cleanly distinguished. We have central plus stabilized regular elliptic for G, plus the hyperbolic, which we haven't touched, plus the unipotent, which now only has the kappa equals 0 piece. And on the spectral side, what we have is the discrete spectrum that we care most about, continuous 0, but now only the trivial eta contribution to it from the trivial character, minus a quarter, the sum over t has now moved over here, stable trace formula for t, ft, but only the part where theta, the part where theta is not equal to 1, the part where theta is equal to 1 went against those guys, plus still continuous 1 and continuous 2. So this is still all spectral, this is still all geometric. This is where we're at right now. So let me tell you what the next step is. I probably will just have time to wave my hands, but I'll tell you what the next step is, and then I'm going to tell you what this means for the final result, and then I'll see how many minutes I have left to tell you how the next step works. Okay, so here is the final manipulation. Let me record it as a lemma. The lemma is that hyperbolic plus unipotent kappa equals 1 minus continuous 2 is a stable distribution. This is the part where you start mixing geometric and spectral terms in order to obtain stability. So I have to take continuous 2 from here, I have to move it up here and combine it with unipotent. I guess I wrote 0 and not 1. Move it to here, and that would give you a stable distribution. Now, let's believe this for a moment, and let me say then what this means. So then the theorem, which is the stable trace formula for SL2, well, I don't know what Langlands thinks it would be. So in my mind, these are the two statements of the theorem. Statement number 1 is the distribution RF minus sum over T STF for T Ft at theta not equal to 1 is stable, which is not an obvious statement. It is an expected statement if you believe in the conjectures, but it's not an obvious statement. Why is it an expected statement? Well, you expect the discrete spectrum to break into packets. A packet will have either one element, locally, let's look locally, a packet will locally either have one element, then its character is conjectured to be stable, so that should contribute to stable distribution. Or a packet has more than one element. If it has, but remember, from the local discussion, an L packet is in bijection with irreducible representations of the centralizer group. Well, that means the centralizer group is non-trivial. But that means if you take an element of the centralizer group, that would give you an endoscopic group. Well, what endoscopic group could it possibly give you? It has to be one of these endoscopic tori. And so then you can take this L packet and then write it, you can create from it a stable character, if you like the sum of the individual characters, and then an unstable character, a weighted sum or a negative sum. The negative sum by the endoscopic character identities is exactly going to go against this one. So this is going to cancel the unstable part in here, and that's going to leave you with the stable part. And this is now a theorem after you have gone through the entire trace formula. So this is the first statement. And the second statement of the trace formula is that this, well, it's obvious from this equation over there, this distribution, the stable distribution, is equal to the following distribution, and I'm going to collect just the terms. So central plus regular elliptic for G, F plus, let me open a bracket here and put this part here, hyperbolic, unipotent kappa 0, minus CTS2, and then minus, or let's say plus, which way? No, it's minus CTS1, and then minus CTS0, eta equals 0. where all summands are stable. That is, we took this stable distribution and wrote it as a sum of stable parts. This is obviously stable, this is proved to be stable. This is stable just by staring at it, because all it has is this part without an intertwining operator, and that's stable just as we explained here by this remark. And then this is stable because we discussed here. Okay, so this is what the statement of the stable trace formula is, the fact that you have this stable distribution and that it's equal to this one. And so so how do you prove this? Well, let's see how much I can write about this. This is where a lot of the local computations go in that I can only quote. But what is the time even? Well, how much minutes can I take for this, or should I just? Okay. Well, but you stop me then, because I don't know what time I'm on. All right. Okay. So, what is it that we want to do? We need to analyze the following thing. So hyperbolic minus hyperbolic to the g plus unipotent kappa 0 minus unipotent kappa 0 to the g minus CTS2 plus CTS2 to the g. What is g? Well, g here is in GL2 of A, and it's going to affect stable conjugacy, because we're in this very simple situation where stable conjugacy is affected by conjugation of the GL2. And a term to the g applied to a test function f simply means that term applied to f to the g, and then f to the g at gamma is f of g gamma g inverse. So this is what this notation means. So now we have to analyze all of these things. The point is that none of these individual differences is going to be 0 on its own, but they're going to combine to give you something that is 0. All right, so let's look at continuous 2. Continuous 2, I'll remind you, is the following friendly expression. Okay, and so now we have to understand what is the difference between these two things. Well, the one thing that I've already noticed a couple of times is this is stable, so really the instability comes from these intertwining operators. So if we write continuous 2 minus continuous 2 to the g, we're going to find that we have this sum 1 over 4 pi integral over d0, and then there will be a difference between this part, let me call it star. There will be star of f minus star, it's an fv to the g, times product over w not equal to v, and then this remains the same, eta w fw d eta. And now here comes another local computation. This is a local problem here, understanding how unstable this piece here is. And the local computation is telling you that star fv minus star fv to the g is equal to the following expression: trace of rho at eta v fv times an operator that I need to define minus the same thing but for the inverted character. And then here n of GV is an operator acting on this space, is multiplication by ln beta of GV. The beta is, I explained earlier. And so now, since we're integrating over D0, eta and eta inverse are going to come both along in the integral, so we can just collapse the two against 1, 2 in this 4. And so we're going to write this entire thing here as a sum over v 1 over 2 pi integral over d0, and then trace rho eta v fv and gv, and then product over w not equal to v trace rho eta w fw d eta. Okay, and so now we give these fellows names. This is going to be h eta v, and this is the other one is going to be I or hv eta v, and this is going to be iw eta w. Okay, so let me recap. It's continuous 2 minus continuous 2g is equal to the sum over v. Well, 1 over 2 pi can come in front. Sum over v, integral over d0, hv, eta v, product w not equal to v, iw, eta w. Okay, so this is the end of the discussion of the first term. What yes, this part here is done. What about the other two terms? Well, let me just, instead of going through the entire computation, let me tell you what the result is in those particular cases. So hyperbolic minus hyperbolic to the g is going to be a sum over gamma in f cross without plus minus 1 of sum over v, and here comes the first thing that tells you that something interesting might be happening. There is a local L factor here. Product over w not equal to v, iw check gamma w over L1 fw. In other words, what you see here is the Fourier transform of those fellows over there. It is summed over all elements of f cross, which for me was q cross, but without the two central elements plus and minus 1. And guess what the unipotent part is going to give you? So we have, but not the whole unipotent part, only the kappa equals 0 part. It's going to give you exactly the same thing. And so the sum of these two is going to give you this full thing here. So hip minus hip g plus unip kappa 0 minus unip g kappa 0 is going to be the entire sum over gamma f cross, and then sum over v h check eta v over the L factor, product w not equal to v iw check gamma w over the L factor. Now look at this. Look at this. Remember what d0 was? And now write the following. Look at the exact sequence the dual of this is d0. So you're integrating over the dual of this, or you're summing over this the Fourier transform. But now you have Poisson summation. In a slightly maybe more general version, it says the following. If 1, A, B, C, 1 is an exact sequence of locally compact abelian groups, and you have a function, a pleasantly behaved function, which of course Ali is going to start laughing because a lot of the sweat he is pouring into is the fact that the functions are not pleasantly behaved. If f from B to C is pleasant, then, or sufficiently not unpleasant, then the integral over A, f of A dA, is equal to the integral over C check, f check of psi d psi, where the measures can all be chosen compatibly. So you choose randomly the measures on A and B. That gives you a measure on C, but that also gives you measures on A check, B check, and C check by duality, because you want double Fourier transform to give you the same function up to inversion. And so you have the measure on A and C check, but you also have the measure on B that's hiding in the Fourier transform, so everything balances out. And so when you apply this to this problem, you see that the three things cancel out and you get 0. So now I'll stop here. This is called lunch silence.
Yeah. I think Tasho, very hard work. Beautiful lecture.
Thank you.